Can everyone hear me fine? Yeah, cool. Okay, thank you. So, yes, as Tobias said, I'm the founder and chief data scientist of NumberBoost. We build AI solutions. We're around 10 people, and we do quite a lot of work in the computer vision space. So, deep learning for computer vision. So firstly, please put your hand up if you've ever used a neural network before. Hi, higher. Okay, keep them up if you've ever used a neural network for a computer vision problem. Okay, keep them up if you've used like a very deep model for a computer vision problem. Okay, nice. Hey. Okay, cool. So firstly, I suggest that everyone check out the Deep Learning Indaba. I've already posted the slides on my Twitter, but wait until after or you'll spoiler alert yourself. So all the links are in my slides. So I strongly suggest checking this out. The Deep Learning Indaba big conference ran in Joburg 2 weeks ago, and Nando de Freitas from DeepMind presented some stuff on convolutional neural networks. He'll explain this way better than I could hope to, but yeah, just further reading. So, deep learning for computer vision. Deep learning is very sexy these days. This is probably the only time you're going to see the word sexy in a presentation today. And it's sexy for a reason. So, the sort of hello world of computer vision problems is this MNIST data set where you're trying to recognize handwritten digits. And the GIF, or GIF if you prefer, is LeNet. So Jan LeCun, who's one of the sort of like forefathers of deep learning, some work he did at AT&T to recognize postal codes on letters. Now, what's crazy is using the link at the bottom, there's a Python script, a Keras implementation of a convolutional network to solve this problem that gets 99.25% test accuracy in like 3 minutes with 70 lines of code. And a lot of that's like comments and stuff. So yeah, it's crazy. So image classification can be posed as like, what is in this image? Is this dog or KFC? Or more broadly, like out of a larger set of possible classes, what is this image? So this is from the ImageNet paper, which we'll come back to later, where you're trying to classify an image as one of 1,000 classes. But there's more to computer vision than just image classification. So object detection is sort of like one level more difficult than image classification. And the state of the art in object recognition is remarkable. So for instance, this is running in real time on frames of a movie, and not just any movie, James Bond, which to me is just crazy. So this I saw on Reddit a couple of days ago. So this is some unknown place in China, probably leaked from like government surveillance network, tracking like people, classifying them into genders, stuff like that. And then the more interesting state of the art stuff is around like mapping images and words into similar vector spaces, or take an image and generate captions of it. And in fact, you can also look at which part of the image the model is paying attention to when it generates that part of the caption. And you can also do stuff with image QA. So given an image, ask a question of it. And it's not just memorizing, because umbrellas are usually up, but in that case, they're not. In the paper, there's an example with a bunch of bananas, and it asks the question, what color are these bananas? And if it just memorized that bananas are yellow, it would have said yellow, but in the image, they were green, and it got it right. And in fact, one step beyond that is video QA. So given the frames of those images, you couldn't answer the question, is this woman packing or unpacking? But if you have the sequence of frames in the form of a video, then you can. There's also some crazy stuff happening in generative models. So given a hand-drawn picture, generate what that would look like if it were a photo, which you can imagine, like if you're an architect or something and you want to quickly see what this might look like photorealistically, you can just draw like a window frame or draw a new window, which is nuts. And then you can apply these sorts of things to video. So this is sort of the primitive example. There's also one with Trump, but I'll show you an example that came out a couple of days ago in a couple of slides. And the same sort of technique can be applied to automatic colorization. So the top is an old school movie from 1954 in black and white. The bottom one is remastered painstakingly by hand. And you can imagine how soul destroying this must be. And the one in the middle is the output of that same generative model for automatic colorization. And then there's a lot of interesting stuff in style transfer. You might have seen Prisma that lets you take a photo and turn it into a painting in a certain style. As Dries showed earlier, there's this crazy horse zebra example. And on the sort of like fake news.
To demonstrate the power of the method, we apply the same input speech mapped to 4 different target videos. Note that all 4 are synthetic and have different lighting conditions.
The auto industry, to help families refinance their homes, to invest in things like high-tech manufacturing, clean energy, and the infrastructure that creates good new jobs.
So this is the same kind of model as the pix-to-pix case, but they're learning to lip sync the input audio. And then you can separately generate realistic sounding audio using WaveNet and generate fake news, but real fake news, not Facebook sharing kind of fake news. So Dries said that there's a magic box in between your inputs and your outputs. I'm going to try to dispel that and point out that deep learning isn't magic. It's actually kind of easy if you can see through all the jargon and complexity that people like to put forward, because then it makes them look smart. So we're going to cover sort of from the bottom up. What is a neural network? What is a convolutional neural network? How do you use a convolutional neural network? Look at some more advanced methods, and then some quick case studies and applications. So what is a neural network? Well, very simply, let's imagine we have 3 inputs, x1, x2, x3, and then we're gonna come up with 3 weights, w1, w2, w3. And initially, those will be just random, and then we'll try to learn the weights that help us predict whatever we're trying to predict. And what we'll do is we'll just take the linear combination of the inputs and the weights, sum them up, and then apply an activation function. Now, there are many different activation functions. I'm kind of just trying to give you a sense of terminology so that when you read stuff later, you're not freaked out. Sigmoid used to be really popular. Now it's popular on the last layer because it maps real numbers to 0 to 1, and probabilities have to be between 0 and 1, and some to 1. But Tanch is sort of similar, but rescaled to -1 and 1, and ReLU just makes the value 0 if it's less than 0, or else keeps it as it is. All of these you can easily compute derivatives of, which is important when you're backpropagating errors and learning weights that solve your problem. So what is a neural network and what is a deep neural network? Well, it's really just sequences of inputs mapping to outputs with these weights and then applying nonlinearity, but then the outputs become the inputs into the next layer. And if you have more than one hidden layer, then it's like a deep neural network. And so the big question is, how does a neural network learn? Well, we need labeled examples. This would be called training data. And so we'll initialize the network weights randomly and initially get random, completely wrong predictions. Then for each labeled training data point, we calculate the error between the predictions right now and the ground truth labels. And then we use backpropagation, which is really just the chain rule, to update the network parameters. So in this case, it'll be like weights and convolutional filters, which will hopefully become clear shortly, in the opposite direction to the error, because we want to reduce the error. And so to throw a scary equation at you, the new weight is just the old weight minus some learning rate times the derivative of the error with respect to the weight, or think the other way around. So here we have our new weight. This is what we're going to update the next time we run an example through the neural network. Is the old weight minus some learning rate, which is just a very small number, times the gradient of the weight with respect to the error. I think it's actually the gradient of the error with respect to the weight. But and that really is just how much does the error increase when we increase this weight. And we're subtracting it because we want to make the error decrease. And so one interpretation, if we just have like one weight and one bias, and I didn't mention bias, but it's just like an input with a value of 1. We might start off here, this little white ball, by randomly initializing our parameters. And then as we backpropagate these errors, the ball hopefully finds a global minimum, or at least a good minimum, and decreases in this error surface. Now we can't see this error surface, and so backpropagation is just trying to like point in the direction of lower error. It's almost like, like it's foggy and you poke a stick and you walk in the direction that decreases the slope. So I really like this TensorFlow Playground example because it lets you build a neural network in your browser. And so here you can change the activation function. We spoke about those. The learning rate you can change. And the problem setting here is we have 2 input variables, x1 and x2. So that would be like x1, that's x2. and we're trying to predict a binary class. So either this point that has x1 and x2 value is blue or it's orange. So this might be like it's fraud or it's not fraud or something. And so here we can like build a neural network in the browser, we can add layers, we can add neurons, and everyone always asks like, how do you pick the optimal architecture? And no one can tell you like a magic formula. Just try a bunch and pick the one that has the lowest error measured on a validation set, which is data that you didn't train on. But I'll just point out, firstly, notice this first weight is initialized at 0.5, and then look at these class boundaries. Notice firstly that these are linear, and these are sort of nonlinear, because the nonlinear activation function. But I'm gonna start training this network quickly. And you'll notice it very quickly learns, but also these boundaries move, and this weight is no longer 0.5, and this loss is decreased, and we're getting like near perfect classification. So, so for more details, see those two links. So what is a convolutional neural network? Well, I'd suggest thinking of it as like an ordinary neural network, but with special types of layers that work well on images. And so, you know, math works on numbers, so we need to convert our image into numbers. And so if you look closely at an old school TV, you'll see there's 3 little dots, there's 3 little color channels. So those pixels are 3 numbers. Each number is in 0 to 255, and an image with a width W and a height H is W times H times 3 numbers. Now, this is an example architecture of a convolutional neural network. This is VGGNet. Now, don't panic. We're going to break it down piece by piece. And we're going to use a different sort of visualization because then we can build it up. And the other image from the paper makes some weird conventions. So let's sort of break this down piece by piece. So first, we need to understand what a convolution is. And I really like this interactive example where we have an input image on the left and an output image on the right. This is just grayscale. In the case of RGB, just apply it to the 3 color channels. And at the top, we have a convolutional filter or a kernel. And so what we do is the 3x3 red blocks on the left, we're going to element-wise multiply those with the values in the kernel. And then sum them up together, which is where you get this 271, and that'll be the value in the output image. And so if you look, as I hover, like on the bottom left, you can see the bottom left are dark because it's hovering over a dark part of the image, and then we're just multiplying the element-wise numbers in the kernel. Now, this is a kernel that we know sharpens images. This is one that we know blurs images. And you can kind of see why it might do that, because we're fading the images around the center pixel. Here's like a Sobel kernel. This is like the Sobel filters are inputs into the canny edge detector, which is like an old school image processing technique. What we're going to do, though, is we're going to learn kernel values that produce different outputs. So it might be useful to detect edges or outlines, but we're going to let the neural network figure out what kernels will help us detect whatever we're trying to classify or solve in our computer vision problem. So put another way, the bottom is the input. I think Dries mentioned padding. So here, just to handle the borders, you can mirror the border pixels or handle that in some way. And the top is the output, and we just slide this kernel. And it's the same kernel that we slide over the whole image, put differently in that little picture. So really, you can think of it as a 2D weighted average. And so we'll slide this kernel over all pixels of the image. And the kernel starts off with random values, and the network will learn the kernel values that help us to map the input image into the labels that we're trying to predict, such that we minimize the error at the end of the day. So it's important to note, again, just that the kernels are shared across the whole image. And that's sort of like, you can think of the kernel as a feature detector, and we want to be able to detect these features regardless of where they are spatially in the image. So one last little interpretation on kernels. One other term for applying a convolution and then the output is called an activation map. And what we're going to do is we're going to apply many kernels. So if we have a 32 by 32 input image, 32 pixels by 32 pixels, and then the 3 color channels, we might do 6 convolutional filters, and then we'll have 6 activation maps, 6 transformations of the input. And so you can think of this as taking your like skinny rectangular input and then lengthening it out. And we'll see in a second how we'll reduce the width and the height as well. And so we have this convolutional layer. So we start off with a color image that might be 224 by 224 by 3, and then we'll transform that into a 64 color channel volume or 64 activation maps. So I'd suggest you check out this paper by Matt Zeiler and Rob Fergus. They won ImageNet in 2013, and Matt Zeiler went on to start Clarify, which is a startup that does computer vision like API stuff. The paper is really cool because they show what these activation maps look like. And remember in the TensorFlow example, we had linear classification boundaries in the first layer. And then the second layer, we pick up nonlinearities. So there you can notice you're detecting little circular shapes, little corner shapes. And the images are examples of images that have high activations in that particular convolution activation map. And as you build up, you can detect like higher abstractions. So you go from detecting circles to detecting eyes to detecting faces, and that kind of thing. Put differently, really these convolutional layers, as you stack them on top of each other, are learning hierarchical features. Now, the other big building block that we need is this idea of a max pooling layer. And I think Dries mentioned this too, but essentially we slide this window and we just take the max number from that window. So here, if we have a max pool of 2 by 2 filters, in each of those 2 by 2 grids, we just take the max number and then use that as our output volume. Now notice we've decreased the number of numbers by, like we now have 25% of the number of numbers because we've halved the width and the height. And so really it's a way of reducing dimensionality from one layer to the next by replacing each n by n sub-area with the max value. And you can think of this as like the network looks at larger regions of the image, sort of zooming out. So instead of looking at the fur, look at the cat kind of thing. And it also helps reduce overfitting because we're throwing away information and therefore helping the network generalize. Now, so we have our convolutions, and then we'll do this max pooling. And notice we still have 64 activation maps, but now we've halved both the width and the height. And so we're going to stack these like convolution max pooling, and go deep. So we'll keep doing this until we have a 7 by 7 by 512 activation volume at the end. And then typically we'll actually flatten that final bottleneck layer because 7 times 7 times 512 is 25088. So it's just stretching it out. And so then we'll add a fully connected dense layer. So this is like the example right at the beginning. We had every input connected to every output in the next layer. We'll fit a dense layer. Now, it's also interesting to note this architecture has become a bit outdated. It's just like it's the easiest to explain, and the more complicated ones aren't that much more complicated. But one thing to notice here is that if you multiply the 25088 by the 4096, you get like 100 million parameters just in that final dense layer. And so like the bulk of the parameters on the end, and there are more efficient architectures that avoid needing to learn so many parameters. But we add this fully connected layer, and then the last piece we need for this architecture is this idea of a softmax layer. So we looked at the softmax activation function, or the sigmoid activation function. And so why we need this is we need to take the final output prediction, which will be Z scores, or like just scores in the real numbers, and we want to convert them to probabilities. And so we'll really just apply the softmax. It then makes every output in the final layer between 0 and 1 such that they sum to 1, and that can be viewed as a probability distribution over the classes that we're predicting. So here, if we think there's a 72% chance or 0.72 probability of this image being a dog, then we'll say this image is a dog. Now, that's sort of what it looks like at a high level with this final softmax layer. But in order to learn these convolutions and the weights and the dense layers, we need labeled training data. So I mentioned ImageNet earlier. ImageNet is sort of like ambiguous in what it means. It could mean the data set, which is 14.5 million odd images in many, many thousands of classes, or it could mean the competition that has run for the last many years and has now moved to Kaggle and is no longer like a big academic conferencey thing, just because the performance has started to plateau. And the competition is to classify an image as one of 1,000 categories, and given 1.2 million training images. Now, if you look at ImageNet, this is just dog category. There's like hunting dogs, working dogs, Dalmatians, poodles. Within the sausage dog category, there's like 42 pages of images. So ImageNet is a lot of data. And so if you look at the top 5 error rate over time, the gray bars are traditional image processing methods. So in 2011, the top 5 error rate was 26%. Then AlexNet, not me, different Alex, fitted a deep learning model with 8 layers and massively reduced that error rate. And then progress sort of like fell off or error rate fell off a cliff. So ZF, that's Xylofergus from that paper I mentioned. Then the GuggleNet with the inception module was sort of like coined with 22 layers. Then ResNet with 152 layers. Now I should point out that human level error rates are around 5%. So in 2015 we already got better than human level accuracy. And then from there it's been sort of ensembles of models, and that's why its progress is sort of flattening out. And so, the 2017 results, the best model had a 2.25% error rate, which is twice as accurate as human level accuracy. So how to use a convolutional neural network? So we'll quickly look at how to use a pre-trained ImageNet winning CNN. So VGGNet, the architecture we've been looking at, came second in 2014. And VGG is the Oxford Visual Geometry group. So it's 16 layers. There's also a 19-layer version. And we'll look at it because it's easy to fine-tune. Now, I'd suggest looking at the link at the bottom for a lot more detail. But we're going to focus on a problem of classifying product images. So I just scraped a bunch of images from a e-commerce retailer's website along with the categories. So there are 9 categories. And it's like watches, jeans, T-shirts, and stuff. The code for this is on my GitHub. Now, we can start with a sort of pre-trained ImageNet model. This is from the Keras docs just because there's more code around like reading files and stuff, which is in the GitHub. But essentially, in that like 10 lines of code, X comments and blank lines, you can use a pre-trained model that was trained on many GPUs for like many, many days or weeks or months to classify your new image as one of those 1,000 ImageNet classes. Now, if we apply that to our clothing problem, we'll classify some of them correctly, like jersey, sweatshirt. But notice, like, there's a category for loafer, like the 5th down, and we have a category for shoes. So we could learn a mapping between like these categories and our categories, because you get a probability distribution over the categories for each image. But a better approach is to use this idea of transfer learning, which is awesome, because someone asked earlier, like, what do you do if you don't have that much data? Use transfer learning. And transfer learning is basically, the approach is to cut off the last layer of a pre-trained ImageNet winning ConvNet, but you'll keep the activation filters that they learned. And these are good for classifying images into one of 1,000 classes. So they're very generic and apply to many different image types. And so then we'll learn to predict new classes by just adding a new final layer and just training the weights on that final layer, keeping the other weights fixed. There are different nuances around how to do this, but that's the sort of idea. And so that's our architecture where we have that final softmax layer in 1,000 classes. What we'll do is we'll pop that off the model and replace it with a softmax layer for 9 classes, which will map our particular problem. And so before fine-tuning, this is just calling .summary on the Keras model object. You have a shape of 1,000 in the final dense layer, and there's 138 million parameters. And then we just pop the layers of the model, and then now we have 9 layers at the end. And if we then fine-tune it, I've sort of said that, you just call model.fit, and in 109 seconds, we get to around 88% validation accuracy. This is training on a GPU in AWS, so it would take longer on your laptop, but it's still pretty fast. Now, 88% accuracy isn't like earth-shattering, but there's points about the data set that mean that there's going to be a ceiling on the accuracy, because there are images in an activewear category that are T-shirts, but they're like Puma T-shirts, and so the model will get that kind of thing wrong. But it couldn't get it right because it's sort of like messy data. Anyway, so fine-tuning is awesome. Insert obligatory brain analogy is just speaking to like, I mean, if I wanted to explain to you that like, that's a box for Superbalist, like you don't have to see 1,000 images of that to learn that it's a box for Superbalist. You bootstrap this idea of a box that you have in your head with the like minor details of that particular box. And this comes up in NLP and a bunch of different application areas as well. So that GitHub repo sort of came from me seeing this. Now, I used to work as a data scientist at Superbalist, and so seeing that Spree added AI to their iOS app, I was like, it's not real AI. And so here you can like crop to a part of the image, and then it finds visually similar products from their database. So you take a photo, that's the like second and third screenshot, and then it finds visually similar products. And you can do this in like an hour pretty easily. So you chop off the last layers of VGG, but you don't add a new softmax. You use the network with those chopped off layers. And you'll use, say, those 4096 activations. Now, you'll pre-compute those activations for every image in your product database, and then compute it for your input image, and then just compute, like find nearest neighbors in that space, or compute the cosine similarity and pick the most similar images. That's sort of what it looks like. The key bit of code is just taking the dot product between those two vectors. And if you run this, that's the input image, and those are the sort of visually similar images that you get. And it's important to note that they're visually similar along different dimensions. So in some of them, it's like a similar color. In others, there's like a graphic in the middle of the T-shirt, and you know, and there are ways to constrain the dimensions of visual similarity. Now, I sort of like emphasize this idea of extracting that dense layer because it's a useful idea for many things. So, for instance, in the MNIST case, you can take those 4096 dimensional vector representations and then run tsne, which is sort of like a low dimensionality, like a dimensionality reduction technique to then visualize high dimensional vectors in sort of like 2 dimensions like this. And you can color them by class, and you can see there's quite a clear separation between the classes based on that final dense representation. Yes. So let's quickly look at some more advanced methods. So if you're doing this stuff in practice, don't use VGG. Use a better architecture. Or even better, use all of them and ensemble your predictions. And then there are many computer vision tasks, as we mentioned. So semantic segmentation is classifying each pixel in the image. Localization is like putting a bounding box. Object detection is just counting instances, like counting objects, but not instances of those objects. Whereas instance segmentation is like, this is person A, this is person B, or dog A and dog B. Semantic segmentation, essentially you take the approach that we've looked at for a convnet, and then you do these tricks to essentially create a deconvolution network. And then you upsample and unpool your input using that bottleneck 7x7x512 representation into finally predicting pixel maps. Object detection, you start off with a convnet, and then you use this idea of a region proposal network where you look at which parts of the image the network is having strong activations, and then create candidate bounding boxes to learn bounding boxes, given like an annotated set of bounding boxes. Style transfer, you have a content image and a style image. And what we're going to do is we're going to take the content image, get that bottleneck representation that encodes the content of that image, much like when we use it for tsne, and then we'll do something slightly more complicated on the style image. We'll compute the gram matrix of a couple layers, but it really encodes like the sort of style of the image. And a function of those two, we can then generate images in the style of the painting, but with the same content semantically. That's sort of what the architecture looks like. I'm not going to go into too much detail, but that's actually starts off with a completely noise image, and then like generates like moves the pixels in the direction such that we minimize this combination of content and style loss. Let's hope this plays.
Can we enhance this?
Can you enhance it?
Hold on a second, I'll enhance.
Zoom in on the door.
Times 10.
Zoom. Move in. More.
Wait, stop.
Stop. Pause it.
Rotate us 75 degrees around the vertical, please.
Stop. And go back to the part about the door again.
Got an image enhancer that can bitmap?
Maybe we can use the predict send method to see into the windows.
This software is state of the art.
The eigenvalue is off.
With the right combination of algorithms.
He's taken illumination algorithms to the next level, and I can use them to enhance this photograph.
Lock on and enlarge the z-axis.
Enhance.
Enhanced.
Enhance. Freeze and enhance.
It's real. So original image downsampled to I think 8x8 pixels, and then use a super resolution method, which is the same kind of GAN architecture as the style transfer. You can reconstruct high-resolution versions from very low-resolution images, such that you like minimize the content loss on that reconstruction. So this image is 3.8 kilobytes, and essentially what you're doing is you're instead of like generating a style image, you're learning how to generate high-resolution images. And it's of course trivially easy to take high-resolution images and generate training data by making them lower resolution, which is crazy because then you can just ship the low-resolution version and the network that does super resolution, and then you save massively on the data transfer because you can just do up resolution on the device. The visual attention stuff is pretty cool. So here, you literally just compute the gradients of the input pixels with respect to the class. This is from the Kaggle distracted driving competition, where it's like, is the person looking at their phone? What are they doing, kind of thing. And then combining that with this image captioning idea, you can do the visual attention thing. Here what we're doing is we're running our image through a convert to get this dense representation. And then much like you do language translation, we have an encoder network and a decoder network, which might be like an LSTM and an LSTM. You run your encoder on the sequence of word vectors for a sentence in, say, English, and then you use the hidden state of the LSTM as a fixed length vector representation of that sentence, and then you have a decoder to generate words in French, say. Now, this is a similar idea, except instead of using an LSTM on the English sentence as your encoder, you're using a convnet as your encoder, and you're using that fixed length representation as the semantic content of the image, and then using an LSTM to generate a description of the image using labeled data. Now, image QA is a similar thing, but you have labeled question-answer pairs. And notice again here, running an LSTM over the sequence, those are actually word vectors, sequence of the word vectors to get a final hidden representation. And then similarly, the image, we get a hidden representation, and then sort of like pointwise multiply, and then softmax against annotated answers. Video QA is kind of crazy how easy this is in Keras. So you run a convnet on each frame, and then you run an LSTM on the sequence of frames, and then similarly have an LSTM on the language side. Now, I wasn't going to talk about this, but Helga mentioned word to vec, and this is like my favorite example in all of computer vision. So basically, word to vec, as Helga mentioned, is a way of embedding words in a semantic vector space. So that might be, say, a 300-dimensional space. And you learn it on a very large corpus of documents, say the whole of Wikipedia or the Common Core corpus. And the idea is that words that occur in similar contexts have similar meanings. So the word king, you'll usually see the male pronoun he or his or him around that word. And in paragraphs where you see king, you'll generally see like castle, knight, queen, and semantically related words. And then you initialize word vectors randomly, those 300-dimensional word vectors, and you try to predict the center word from the context words. You don't have to do any of that, though, because you can download pre-trained word vectors trained on the whole of Wikipedia or the whole of Common Core corpus. And so you get 300-dimensional numbers for each image, and if you use PCA to project that down to 2 dimensions, you see these kind of like really elegant vector operations, where you can take the vector, so first king and queen are nearby in the vector space, so is man and woman, and then you can do this like quite popular example around like king plus woman minus man is approximately, or the nearest neighbor for that resulting vector is queen in that vector space. Now, there was a paper, Tomasz Mikolov sort of invented word to vec, and Jeff Dean, there's this cool page of Jeff Dean quotes on Quora where one is like, Jeff Dean's phone number is the last 10 digits of pi. He's like this Jedi in machine learning. And Joshua Bengio, who's also like one of the forefathers of deep learning. And so basically what this model does is instead of our convnet predicting a one-hot encoding, so here our ground truth labels will be 100% probability that this image is a cat if we know that this image is a cat, 0 for everything else, and we'll try to get our model to predict that. So this devise model, essentially, instead of having our labels as one-hot vectors, we're going to replace the labels with word vectors. And we know the word vector for every noun in ImageNet because we can download that from a separate model. And so you look up the word vector for cat, and instead of predicting a one-hot encoding, you predict this 300-dimensional word vector. And so essentially we're mapping images into this semantic language vector space. And so that lets us do remarkable things. So, well, firstly, if you have, let me hold up on that for a second. So firstly, if you have an image of, say, a violin, and there are violins in ImageNet, then you can detect that like this image is a violin. You can classify it as a violin. But let's say you have an image of a cello, and there's no cello in ImageNet. What you can do is you can run this image through this conv that you've trained on ImageNet. You'll get a resulting word vector, and you look up that word vector's nearest neighbor in the word vector space, and you'll get cello, not violin. So you can literally make predictions on images that are not in sample, or that you don't have annotated labels for, by bootstrapping this external language data set. And you can also do something like this. So you can construct this like word vector star as just the average of the word vector for fish and net, and then get nearest neighbors to this word vector star by pre-computing the word vector representation of every image in ImageNet, not just the 1,000 classes, but every image. And the nearest neighbors are images of fish in nets, which is crazy. And so some quick case studies. So this is stuff that we're working on, like estimating accident repair cost from photos of accident damage. You can imagine how you might do that. Image and video moderations. Doing some work with a big gay dating app that has like tens of millions of users, and hundreds of thousands of photos being uploaded per day. And you can imagine how many of those are dick pics. And people were like manually moderating these. Like fitting the model, I had like hundreds of thousands of dick pics on my laptop. I had to like delete movies to fit more dick pics. I was worried if I dropped my laptop, it would just turn into a fine mist of dick pics. But yeah, so that's like, yeah, fully automated end-to-end image moderation pipeline, and also looking at applying it to video, where again you can just sample the frames. And then medical image segmentation. This was sort of like a data science competition, but you're given the image and a pixel mask, and you try to predict the pixel mask for new images, identifying like pathologies and things like that. Also, it's work in counting people. So here, just point a camera at a store entrance and count the people coming in, but also like classify their age and gender. Reluctant to suggest you should assume their gender, but yeah. What's interesting to me is like you could do this as the store, and you could like put these cameras around the store and create a map of the store, and then know that like the young females tend to spend time in front of the cookie aisle, and other people spend time in front of this aisle. But you could even do this like adversarially, and like point cameras at stores, and then estimate like foot traffic and like trade on their earnings estimates. I mean, there's stuff around doing this with satellite imagery, counting the cars in the parking lot of Walmart kind of thing. So one of the sort of like interesting use cases, I helped organize this deep learning hackathon right after the Deep Learning Indaba, and it was to detect potholes in images. And Stellenbosch University published this paper and let us use the data set, and they used sort of like older school machine learning techniques, and they got around 78% accuracy. People at the hackathon worked in teams of up to 5, but one guy on his own managed to get to 85% accuracy in one day, which is going from a 22% error rate to 15% error rate, which is crazy. We're also doing some work on like extracting products from catalogs and cropping to products and extracting the prices from the catalogs, and looking at the sort of like real-time ATM video classification on security cameras. This isn't anything we're working on, but I already like this example. So if I can find my mouse, hold on. There you go. So these are chips going down a sort of like industrial production line, and these very like high-powered air jets shoot the reject chips off the line, like really, really fast, which is totally crazy. So yeah, sort of last slide, we're hiring Python software engineers and also like machine learning interns and engineers. And that's me, thank you. Get in touch, there's my Twitter, emails.
Cool, thanks, Alex. Yeah, awesome. Sounds great. So if any of you are inspired by that, just a reminder, check out Cape Town Deep Learning on Meetup. We have regular meetups. Come join us. But any questions? We've got 5 to 10 minutes for questions.
Hi. Thanks a lot for the talk. It was very
Pleasure.
inspiring. I was just wondering if you have had any encounter with a technique called zero-shot learning,
Yes.
Basically, the idea of being able to predict affordances of objects.
Yeah.
And how's your experience been with that? Just wondering.
Yeah, so I've like read the paper. We haven't implemented it, so I can't really answer that question with experience. I can just hypothesize that it's hard because it looks hard. Yeah.
Okay, cool. Awesome. Thanks.
Cool.
The image, the example that you showed of super resolution of the faces.
Yeah.
Oh, sorry, a little bit closer. Cool. Were those specifically, was it only capable of increasing the resolution of faces in that example, or can it do it that well for all kinds of images?
All kinds of images.
Even in the example with the 8x8
you've
images.
trained on them like in your training set, if it's seen like a broad enough variety of how to up resolution that image. So like there's an example of like a low res picture of a stop sign that looks like all hexagonal, but it's actually circular. And so like it up resolutions it to a circle kind of thing. But yeah, it's not just faces, it's anything.
That's mind blowing. Thanks.
Cool.
I've done a fair amount of work in image classification with machine learning. Do you know of any kind of open source or government projects in Cape Town, like pothole detection or something like that, which you could work on to improve your skills? Do you know of anything publicly
Yeah, I know
available?
a bunch. Email me and I'll send you some suggestions.
Cool, thank you very much.
Cool.
Hi, Alex.
Hi, Helga.
Nice talk. I enjoyed it.
Cool.
Can you say a bit more about what you do in the case when you have mixed data types? So when you have like an image and some text and maybe some structured data also, like for your products, when you have a product image, but you also have a description of the image, but you might have a price.
Yes.
Size.
So we've actually worked on this. So that hackathon with the potholes was initially going to be with a certain online property company whose name rhymes with NT More, something like that. But then the lawyers were like, no, we can't give you data. But we got pretty far in the process, and I sort of like fitted a toy model using. So the idea was to predict listing prices from images of the listings, descriptions of the listings, and structured data around bedrooms, bathrooms, square foot, postal code, stuff like that. So most people just throw away the images, right? And they probably even throw away the text. They just like fit a model regression on the number of bedrooms, square foot, and stuff like that. You could then include the text by running word to vec and then doing document vectors or fitting LSTMs on the sequence of the description, like a cute fixer-upper versus like a charming something. But then you can bring the images into it by doing that dense encoding process I talked about. Then you can concatenate all the images, say. But then now you've got the vector, you've got the inputs in your neural network for the structured data, and you've got the inputs for the description, that fixed length LSTM, and then you've got these concatenated fixed dimensional representations of the image, and you just fit a network on top of that. So you just put all that as your inputs, and then you fit a model on top of that. There's some stuff also like to predict, for example, like where a taxi will go given past taxi trips. You can fit this model as like an autoencoder, and then right at the end, then add in like some additional data. So you can really just like compose things as however you like, provided you can backpropagate the errors.
Cool. Any other questions? Okay, then let's thank Alex again for an inspiring talk.